We're returning to chapter 9. I know it looks like we're jumping around a little, which we are, but there's a reason for it. We're now going to look at the sampling distribution of means. So you've got your population, so we're used to this. And this is everybody of interest. And over here, we got a small group, which is our sample. Only in this world, we are interested in a parameter called mu. We have talked about this last time. What is mu calculating? What is mu? It's the Greek letter mu, but what is it when you talk about the population mu equals 20? What is that?
The average mean.
Yeah. So it's the population mean. And it's called a parameter, right? And less so, there's a guy called sigma. And it's also a parameter, isn't it? So sigma is a parameter. Oh, that's how you say them out loud. Can you remember what sigma represents in a population? If mu is the mean, what is sigma? It's the population
Standard deviation.
Standard deviation.
That's the guy. Now, if we move over to a sample, which we have here, if this is a fair representative sample, don't we call numbers that you get from a sample a statistic? Just like, remember, p hat was a statistic, right? If you wanted to get the statistic and it was the mean, don't we use that guy called x bar, right? That's the symbol we use for the mean, right? X with a little line up on it, x bar. And what letter do we use for a sample standard deviation? We actually have a couple of choices here because we use different ones sometimes. If I wanted to do the standard deviation of a sample, what kind of ways would I describe it? X bar would be for the mean, right? What would the standard deviation be? There's 3 that I've used.
SD.
Right, standard deviation. I've also used S sometimes, haven't I? Maybe not as common. And on your calculator, don't you very often get S with little baby X? Those are the same thing. It just depends on what day of the week it is, which one you want to use, but they're all the same thing. When you use those 3 things, don't we typically mean the standard deviation of the sample? So far, so good. Now, just like we did with proportions, we're going to look at what would happen if you, say, took a sample size of 100. Well, suppose I was interested in the average age of Americans, right? Suppose that was what I was interested in. And I took a sample of 100 and I got the answer 35. So I collected 100 random people in America. I got their age and added them all up, divided by 100, and the average came out as 35 years old. Is that the same as the entire population of America's average age? No. Would we expect it to be close most of the time? Yeah. Reasonably, right? But we wouldn't expect it to be 35. Now, just like we did with the other one, if I did another sample of a different 100 people, couldn't the next time the answer be 33, or actually, let's say 33.5, right? And then I did it a third time. And after the third time I did it, maybe the answer was 36. Now, the sampling distribution means what would happen if you kept on doing it over and over and over again until you get bored? Well, you'd get a whole lot of different answers. But if you did it often enough, quite a few of them would be the same answer, at least to one decimal place. And when you get a shape that looks like that guy, and right, a normal distribution, right? A bell shape, symmetric, there's two other names for it. But right there, wouldn't that be mu, the population mean? Right, if you did it often enough, wouldn't the most likely answer, right, the most common answer in your sample, wouldn't that match the population mean? At least that's what the theory says. So for a sampling distribution, so if you took lots and lots of samples, say of size 100, it would be normal in shape, and it would have a mean equal to the population mean, and it would have a standard deviation. Now, when we did the standard deviation for proportions, didn't the formula have a square root in it, right? You remember that guy? It was the square root of p, 1 minus p over n. Remember that ugly, weird guy? There is a formula for these guys. And the sampling distribution has a standard deviation of sigma divided by the square root of n. So can you imagine going 1, 2, 3 standard deviations, 1, 2, 3 standard deviations? That would be the typical spread of a sample like this. So far, so good? Right. Now, the types of questions you're going to get are going to be find confidence intervals again, right? And we're going to do them the empirical way. That's the 1, 2, 3 standard deviation way. And then later on, we're going to do it with SALT, which gets you much more accurate results. So we're going to do things like that. And we're going to use samples to estimate what that confidence interval looked like. So let's do a theoretical one first, because that's the important thing. When you have data that is normal in shape, so can you imagine the population of Americans? Would it be reasonable to assume that it might have a shape that looks like that, right? It's normal in shape. If you have that, and two, if the sample is big enough. And I was trying to find out what this book thinks big enough is. So I'll tell you what I consider big enough. You need to have at least 30 numbers, right? You have to ask at least 30 people. If this is true, then the sampling distribution is normal in shape. So that means it looks like this. It's normal in shape with a mean equal to the population mean and a standard deviation equal to sigma over root n. So if you have data that is normal in shape and the sample is big enough means 30 or more, then the sampling distribution, right, will have this shape. It'll be normal as well, and its mean will be the same as the population mean, and its standard deviation will be this guy. So let's give you an example. Suppose we know that the population mean for IQs is 100, and that the standard deviation for IQs is 15. Because actually we've used that before, right? Suppose we know that. So what would sampling distribution for a sample of 50 look like? Well, wouldn't it have a mean of 100? And wouldn't it have a standard deviation of sigma over root n? 15 over the square root of 50. And we do 15 divided by the square root of 50. And that's about 2.12. So can you imagine a question where they tell you everything you need to know about the population, and they just ask you to look at a sampling distribution for a data size, in this case of 50, right? Maybe the next time the sample is going to be 100 or 42, right? And maybe they'll sneak in a sample of 8 and ask you why you can't do it. And you're going to say, it's too small, right? So it has to be big enough. Or maybe they'll give you a sample where the data is definitely not normal in shape, right? Can you imagine data that had 2 humps in it because they showed you a picture of it? Or it's very skewed to the left or very skewed to the right? Would you then say, you can't do this because it's the wrong shape, right? Now, I'm not sure which one is which. I'm 90% I know. This is going to be number 1, and this is going to be number 2. So let's look at some homework questions to just start off with the theory. Nothing too deep, but basically getting us to look at sampling distributions. Right, now here we go. Can I make this bigger? Okay, that's as big as it can go. Explain whether one or both of the situations for approximate normality of a sampling distribution holds. So number 1 is the original population is normal in shape, right? And the second one is that it's big enough, right? Whatever big enough means. The mean body temperature will be determined from a randomly selected sample of 18 individuals. Okay. We're about to find out if big enough is 30, because it might be 10. And it's Fahrenheit. So we do know that this is approximately normal in shape, don't we? Because they tell us that in the instruction. So here goes. The population of temperatures is bell-shaped. However, the sample size is small. That's the answer I'm picking, because isn't 18 less than 30? Right. So now I'm going to check and find out whether 18 is okay for them. And guess what? We agree, at least for 18, right? The mean number of books owned will be determined from a random selected sample of 4 college students. I'm not even going near that one. 4. Sample too small? Definitely sure, right? And guess what? It's skewed to the right. Doesn't it fail on both then? So you just go through this one. Oh, well, I should put the thing off. Can you see? It's neither of the 2 situations, so it fails on both. So you can fail on one or the other, or you can fail on both. Let's take that out because it's distracting to see the answers. Have you noticed in that question, it's really just getting an idea of when you can use a sampling distribution, right? You've got to have a normal shape in the population, and the sample's going to be big enough. And big enough is 30 or more, at least by my definition. Now, in question 2, suppose that a large population of students, the mean amount of sleep is 7, and that standard deviation is 1.5. What is the value of the mean of the sampling distribution? Aren't they basically getting you to realize it's 7? Agreed? Now, this notation here is quite useful. I haven't used it yet, so I might as well talk about it. This is the standard deviation of the sample. I just called it SD, but SD X bar, right? Isn't that going to be sigma, which is 1.5, divided by the square root of 260? To remember my formula, sigma over root n. And so I go to my calculator and I do 1.5 and I divide it by the square root of 260. And the answer I get is 0.09. What do they want? 3 decimal places. So 0.093. And we're done. Are we comfortable so far? Right, now I'm going to leave these guys for a minute and do it on paper because I think you need to see some calculations now. So I'm still working on question 2. Once I get into the screen, here we go. Now in question 2, you know that the mean was 7, that the population standard deviation was 1.5, and that the sample was 260 students. And we already found the standard deviation of the sample, right? Which is this guy. And it ended up being 0.093. So far. Now, in the next question, although you can't see it, it's question C. They want us to use what they call the empirical rule. And they want you to use it to find a 68% interval. They don't even call it a confidence interval, but that's fine. It's still 68%, right? Now, won't that be the mean, which in this case is 7, plus or minus 1 standard deviation? That's 68%. What will I do if I want to find a 95% confidence interval? How many of these guys do I use? $68 is 1, 90, that's it, 2, I say now, 0.093. And 99.7, what do we get? It's 3 of those guys. Isn't this very, very similar to what you did with proportions, but now you're doing it with means, right? 1 gets you 68, 2 standard deviations get you 95, 3 standard deviations approximately get you 99.7. So in this case, it would be 6.907 to 7.093. In this one, you double that, so what would that be? It'd be 7 plus or minus 0.186. And so that would be 6.814 to 7.186. And this one would be 7 plus or minus 972, that guy. And so it would be 6.721 to 7.279. Are we comfortable with finding 68, 95, and 99.7 guys using the 1, 2, 3 standard deviations? By the way, to get this guy, just to remind you what it was, that's the formula for it. in this case 7 over the square root of 260, which better be that guy. Okay, let's do question 4. I'll tell you why I was pausing. I was reading 3 and I didn't like it. N equals 85. So a randomly selected sample of 85 individuals over 65. We're taking a memorization skill or test. I guess I would probably call it a test. And the sample mean was 53, so that's the score they got. And the standard deviation is 7.3. And we are being asked to calculate the standard error of the sampling distribution. Now, that's this guy, agreed? Sigma over root n. But we don't know the population mean, and we don't know the population standard deviation. We just know these guys, right? So how can we get that? Well, when you don't have the numbers that you want, can't you at least use the numbers that you've got? What does that mean? It means that won't you just use the standard deviation divided by that? Right, I don't know the population standard deviation, but don't I know at least the sample standard deviation? So that will do as an estimate of the real answer. So if we go 7.3 divided by the square root of 85, we're going to get about 0.792. So what we're doing is that we're taking this guy here and we're replacing them with those guys. Now, in a way, isn't that really more realistic? I mean, why would you bother picking a sample if you already knew the population numbers? Wouldn't it be a pointless exercise? I know what the average age of Americans is. I've asked them all. Right? Isn't it more realistic? I don't know what the answer is, so I'm going to ask 85 of them and see what I can come up with, right? That kind of idea. So in reality, we use as an approximation for the sampling distribution. We use that guy. And for the mean, we use that guy. Now, will it be perfect? No. But experience has told us that it is pretty likely to be darn close to the right numbers. And it's either that or you can't do anything, right? So you have to compromise. So the approximation for sampling distribution is basically just using the sample standard deviation divided by the square root of n and the mean. Are we good with that? Right. Same formula, equivalence. Can you remember doing population ones? Didn't we do square root of p 1 minus p over n until we didn't know what p is, and then we called it p hat 1 minus p hat over n. Do you know you only get one or the other? So whatever one they give you, you use it, right? If you tell me p, I'll use it. If you tell me p hat, I'll use it. If you tell me what sigma is, I'll use it. If you don't know what sigma is, but you only tell me who S is, I will use that instead. And it's been found to be pretty good. And so we keep using it because it's been effective. Now, why was I pausing over question 3? Here is the reason I'm pausing over question 3. What is the problem with those two sample sizes?
They're too small.
They're too small. Yeah, guess what WebAssign told us to do? Still use them to get the standard deviations. Do you know if you're going to have a rule, shouldn't you stick to it? If I ever meet the guy who wrote this, I'm going to tell him I was doing this question and did this. Now, let's be generous. You know that WebAssign is a computer software and it randomly generates numbers for every question. You might go to question 2 and the numbers are 42 and 51 and you're going to be quite happy with them because they're big enough, right? And I got landed with 16 and 4 and I'm not happy with them. So you do it because they tell you to do it, but when you realize that in real life, you shouldn't be doing any of the sampling distribution stuff, right? You shouldn't be doing that. There is a way to cope with small data sets, and we will show you that, right? But that's in the next section, right? There's a thing called the student T distribution, which is what do you do if your sample's small, or what do you do if the shape isn't normal, right? What do you do if one or both, you know, the properties that you need don't work? Then you use this other guy called the student T distribution, and that works, right? So that's what I would have used. Oh, we can talk about the answer to this. I don't even care about the numbers, but which one of these two do you think is going to have the biggest sampling error? The 4 or the 16? What's going to have the biggest error? Standard error, Sam, this guy.
4.
Agreed. Because isn't dividing by the square root of 4 going to be a bigger answer than dividing by the square root of 16? Agreed? So small samples, big standard deviation. They call it standard error, but it's also the standard deviation, right? Big samples, small. So this would be big and this would be small. If I did 16,000, wouldn't the standard error be tiny? Because dividing something by the square root of 16,000, would you agree that would be a tiny, tiny number? Wouldn't that also give you very small confidence intervals? Which means that you would know really within a lot of accuracy where the real answer lived. So let's try that. I am interested in the average height of American adults. And so I go and I collect a good sample of 200. And I'm making the assumption that American adults are normally distributed, which is pretty reasonable. And in my sample, the mean was 69 inches and the standard deviation of my sample was 5 inches. And I would like a 95% confidence interval using the empirical rule. So that's our story. I want to know what the average height of Americans is. I collected a nice random sample of 200 and got this data, and I would like to use it to get a 95% confidence interval, essentially, right? Some range of numbers that I'm 95% sure the average American height is in. But the standard error of the sample is going to be S over the square root of n. It's going to be 5 over the square root of 200. And so the standard error, 5 divided by the square root of 200, is about 0.354. Now, if you want to do a 95% confidence interval, it's going to be the mean, because that's the only guy we've got to work with, plus or minus how many How many? Oh, just said the answer thing. 2 times the standard error. So if this was good data, it would be, what would that be? 69 plus or minus 2 lots of this guy. So it'd be 69 plus or minus 0.708. So it would be 68.292 up to 69.708. And would you agree that's a pretty small range, right? Give or take an inch or two, right? From start to finish. If this was good data, do you know you'd only need to get about a sample size of 200 to be within an inch of the real answer? Isn't that pretty impressive how little you need to ask to get pretty good data? Now, if I upped that interval, which I'm not going to do, but imagine I upped it to 20,000. Right, I could do that. This is what your interval would look like. You have to trust me on this. 68.9292 to 69.0708. Would you agree that the answer is darn close? That range is darn close to each other, right? So if I had enough money and I got a good random sample of 20,000 Americans, couldn't I find out their average height, weight, anything that involves calculating means? Couldn't I? And wouldn't I also probably get it with a real degree of accuracy that would be quite amazing? And just to finish off this question, isn't a 95% confidence interval also a 5% wrong? So I could spend all that money, and trust me, isn't 20,000 people a lot of people to pay to go and get their height and people to collect and do all that stuff, right? And there's still a 1 in 20 chance that the data I got wasn't right. It's one of the 5% wrongers. And you just live with it because it's going to happen. You can guarantee it. Okay, let's return back to the homework on the first one. It's a very short section. There's not an awful lot of questions in it. This one is to do with variable names, right? Which one of these symbols in question A represents population mean? Which one of those symbols is the population mean?
Yeah.
Number 5? Great. Okay. Which one of these is the population standard deviation?
Sigma.
Yeah, third one. Now, these are the population ones. Now, it's saying calculate the standard error. Won't the standard error depend on these numbers up here, right? And the standard deviation is that guy, divided by the square root of 28. I'd argue about 28 being big enough, but let's just pretend they're not paying attention to their own rules, right? So it would be 47.71, the standard deviation of the population, divided by the square root of 28, the sample size. Next one. Population mean is 60, standard deviation is 6. For a random selected data, that's a good number, 36, I'm happy with that number. Give the numerical value for the mean. Won't the mean still be 60? Great. Won't the calculation this time be sigma, because I know it, divided by the square root of 36. And I'm so happy they did something I can do in my head. 6 divided by the square root of 36 is 6 divided by 6 is 1, right? Use the empirical rule to find a 95%. So won't that be 60 plus or minus 2 of those guys? So won't you get a 58 and a 62? Agreed? Now, sample speeds for a random of 36 vehicles are measured at this location, and the sample mean is 67. Given answers to part B, explain whether this result is consistent with the belief that the maximum speed is 60. Right. If you would expect the range to be 58 to 62 because the speed limit is 60, I'm assuming, right? What would happen if you watch 36 vehicles and the speed, the average speed is 67? Would you agree it's outside the expected range? Isn't 67 bigger than the 58 to 62, which is what you would expect the average to be, right? So the sample mean of 67 would not be consistent with the population mean being 60. It is outside the range of possible values. Now, what that is, it's a bit like an experiment where you make an assumption. Yeah, this road here, the usual traffic speed 60. For whatever reason, you decided that, right? That's what you thought it was. You then did a sample and you go, oh, if my assumption of 60 was correct, sometimes you get a little bit more, sometimes you get a little bit less. The kind of range you would expect to happen 95% of the time is 58 to 62. But if you actually did it and you got a 67, wouldn't that be evidence that your assumption of 60 miles an hour is wrong? In other words, you set up a hypothesis and then you get data and you see whether the data backs you up or whether the data contradicts you. I mean, in the scientific world, isn't that kind of how they do things? They have a theory about what something should be. Like, I believe that quasar stars should blink at a certain range of values, right? The physics tells me that. And then people go out and they measure quasar stars and what speed they blink at. And after they come back with a sample of 200 of them, they say, well, your theory says that most of them should be in the range 20 to 40, right? The average should be around about 20 to 40. And we did a sample of 200 and it was 82. Isn't your theory just wrong then, right? Your theory doesn't match the observed data. And so people say, oh, well, we'll have to figure a different theory for what makes pulsars blink. Actually, pulsars do blink. It's not that they physically blink, it's they rotate. And when they're near you, you see them bright. And when they're jets of gas aren't near you, pointing the other way, they look dimmer. So it looks like they're blinking. Useless piece of information, that, but I thought I'd tell you. Right, number 7, describe the sampling distribution for the statistic of interest in each of the following. Okay, so we got a story and we have a sample size which is far too small, but I'm not going to go there anymore. A fisherman takes tourists out fishing and he noticed that over the long run, the weight of certain type of fish that is typically caught is approximately normal with a mean of 13 and a standard deviation of 3. So hasn't he told us mu is 13 and sigma is 3? During a good day, a boatload of 8 people catch the limit of 2 fish each, or in other words, a sample of 16. There they go and break my rule. The statistic of interest is the mean weight of the 16 fish caught, okay? The sampling distribution of the mean weight of 16 fish is approximately a normal curve. The mean of the sampling thing should be 13. And the standard deviation should be 3 divided by the square root of 16, which actually is 3/4. So in that story, if we assume that 16 is big enough, which I don't, but if we do, then isn't that where we would go? Now, if we do question B, haven't they upped the number to 60? Wouldn't that basically only change the sampling distribution's standard deviation? Because it would now be a different story, but it would be 4, because where is it? Population standard deviation is 4, and it would be divided by 60, and that would be the answer to that one. I really wish for this question they gave you the option of saying no, that the sample size is too small. I wish they'd given us that option. I'm quite happy with this one. Would you agree 60 is plenty? You can do it with 60. I'm not comfortable with it doing it with only 16 in your sample. Let me try something on this, just in case they did do that. Oh, well, that's just because of this. Yeah, they're allowing 16. So in real life, samples have to be bigger than or equal to 30. But in WebAssign, any number seems to work, except when they ask you, is it too big? In which case they then they use the rule. So will we put that down to bad software, that it's allowing numbers that shouldn't be allowed, and just live with it? That's all I can say. Couple of questions to work with. You would be surprised by how generous they are in normal. Does that data look approximately normal to you? And be very generous. The answer is yes. They're counting that. So you might think, what on earth does normal look like? Shouldn't it be a nice, perfect bell shape? Well, yeah, we would love that. But as long as it's approximately normal. Approximately normal. High in the middle, low in the ends. That's all you need. High in the middle, low in the ends. So as bad as that looks, that would count as approximately normal. What about that one? They're calling it close to normal, right? Approximately normal. Oh, darn it. It might be in this section or another one. Can you imagine one that was definitely skewed to the right or left? Then you wouldn't do a normal. And that is us. Time has shot by. Last name, bye-bye. I'll see you tomorrow.
Have a good day, Professor.
You too. Bye-bye.